Okay. All right. Well, welcome back to another tutorial. Today is tutorial number 9 on the Symbolic Toolbox. So we're going to be looking at how to make equations, how to evaluate them, do some calculus and some derivatives and integrals and stuff. Okay. So again, this is chapter 12. If you want to see more information in the More handbook book. All right, so the way we're going to do this is first is we're going to make a variable or make an equation. And so what you're going to do is you're going to type syms space t, so S-Y-M-S-T. Then you're going to make an equation, so y equals t squared plus t plus 10. Okay, so with this equation that I have right here, if I run it and I look at y, it is now in a symbolic form, okay? So you can, if you wanted to, make, let me scroll up here, syms, another equation with multiple variables by doing this, okay? So this now is another equation, okay, that just uses x, t, and c as symbolic forms, okay? Now, if I just comment this, just to show you, say we want to evaluate this one above at 19 seconds. Well, the way to do that is to plug in t of 19 after your equation and then say eval of y. So when you run it, it now will spit the answer out. It evaluates this equation when the time is 19. It's pretty cool. Okay, so well, now let's look at the solve function. Okay, so what we're going to do, copy and paste this, is we want to solve x squared equals 9. So what you do first is you rewrite the equation so it's x squared minus 9 equals 0. And I'm just going to clear everything, so I want to start fresh. I'm going to make an equation where I'm using x as my equation. So I do syms x. Then I do equation equals x squared minus 9. Then I'm going to say x solution equals x squared minus 9. And then I'm going to say, whoops, I didn't mean to do that. I'm going to say solve of equation. Okay. So here's my equation. So it's minus 0. Okay. I just said, okay, that's the left-hand side here. Then I'm going to solve the equation. So let me make sure this is suppressed and run it. And now I have minus 3 and 3. Those are my answers, okay, which makes sense. So, showed you how to create an equation by using syms. Showed you how to solve one equation. Now let's solve two equations for two unknowns, okay? So we want to solve the system of equations, 5x plus 6y equals 7, and x plus y equals 2. Okay, so two random equations. So the first thing you're going to do is you're going to, again, this is, I just cleared everything, make the syms of x and y, make equation 1, which is 5x plus 6y minus 7. Okay, so I make sure I bring it so that it's all equal to 0. My second equation is x plus y minus 2. Okay. Then I'm going to say answer equals solve of equation 1, equation 2. Okay. And let me run this. Now, if I type answer, it gives me this weird structure field. Okay. Well, the way to extract that, okay, is you say x equals eval of answer dot x. Okay. So what this dot is doing, click enter, is it's getting the correct answer for X out of answer. Okay. So when I run this now, it will spit out a number for me now. Okay. Do the same thing for Y. Eval answer.y. This is how you actually have to grab those values. Okay. A lot of the coding has to do with understanding how to grab that. Okay. So if we check the answer, 5 times 5 is 25, plus 6 times -3, which is 18. Okay, minus 7, that's 25, and then you get 0. Okay, so if I do 5 times x plus 6 times y minus 7, you get 0. Okay, so that's how you solve. You can solve 2 equations, 3 equations, 4 equations, whatever you need. Okay, we put semicolons on here. Let's now look at differentiation. So let's call this C. Okay, so clear all, CLC, sims x, y equals x squared plus x. We're going to find the differential or the derivative of this. Okay. So again, create an equation. So we're using sims. Here's y. And what I want to do now is find dy dx, which is the slope of that line or the first derivative. So dy dx, I'll call it like this, is just diff of y. That's Matlab's built-in function to find the derivative of this. Okay. And when I run it, it should give me 2x plus 1. Okay, that's the derivative. All right, if you remember from calculus, you take the exponent and you multiply by in front and you subtract 1, so that becomes 2x. And if it's just to the power of 1, it's just whatever the constant is right here, which is 1. Okay. Okay, so say we want to find the second derivative, dy, so d squared y dx squared. Well, then you just do this. If y comma 2. Okay. This should be, if you take the derivative of this one, it should be 2. Okay, so the answer is 2. All right. So that's how to find that. Okay. So say we want to find multiple derivatives at one time. Well, let's make a column here. Take that off. Okay, so again, I make a new equation. I can clear all, CLC, and make sims x. Okay, so here what I have is 1 equation, 2 equation, 3 equations. Okay, so I can put those in a matrix and do the differential of y, which is all of these, and you'll get basically each answer. Okay, just a quicker way instead of writing multiple lines. Okay, so these will tell you the derivatives of these functions. Okay, pretty fast and much more efficient in doing this than trying to write more than one line. Okay. All right, cool. Let's talk about integration. Okay, so here we have integration. Again, I just cleared everything. We want to find the integral of x squared. So again, sims of x. Just make an equation. Okay, and let's just make it easier. Let's just call it y. And let me put y here. So our equation is y squared. We want to find the integral, which is you just type int and then put in parentheses your equation. So I'll run it. Okay, so you get x cubed plus 1. So the way we integrate is we add 1 to the exponent and divide by that. Okay, so it's x cubed over 3. I don't know why I said plus 1 if I said that. I'm sorry. X cubed divided by 3. Okay. Say we want to do this, so we want to integrate from one value to the next. Okay. Well, we could say comma 1 comma 5. Okay, so that's going to integrate from maybe 1 meter to 5 meters. Okay, so that's how we put our limits in there, and it should give us a number now. Okay, so 124. Now, if you want to correctly have that number in decimal, you have to say eval. So it won't give you, it'll actually give you a number. It won't give you a fraction. Okay, so I could probably highlight the rest of those. Okay, so 41.333. But what I'm going to do is, that's okay. That's fine. We can keep it running. So let's just do an example. Okay. Because sometimes you get this. Okay. So we want to find the work done to a piston. So the work done by a piston is W equals P dV. So it's really the integral of P dV. Okay, where V is volume, P is pressure. And we're going to assume, I believe, P is constant. Okay. P is the pressure, V is the volume. All right, we're going to go from 1 centimeter cubed to 3 centimeter cubed. Okay, and don't worry about the picture. Basically, I have a piston cylinder device that's moving outward. Okay, so making a variable that's called Sims V. My V1 is 1, V2 is 0.05, 0.05. Okay, that's the first volume and the second volume. Okay, now let's see here. I think you can change these, as I think I messed with this. So let's put this at 3, okay? So initial volume is 1 cubic centimeter, second volume is 3 cubic centimeters, okay? So 1 and 3. Let's assume that it's this pressure, 101,325, okay? Now what we're going to do is we're going to integrate, okay, basically this equation here, okay? So the equation is we have to integrate P, okay? But P is a constant. So if you put in just P, I'll show you here, okay? If you remember my little trick for return. Say we're going to integrate P, okay? All right, so just to review, what we're doing here is we're integrating this equation, which is P from these change in volumes, okay? But P is a constant, so we're going to do this. Now, if you integrate EQ on the equation, you're going to get this, watch, okay? All right, so it didn't work, okay? Because it doesn't have the variable that we're trying to integrate, which is V, okay? All right, so again, remember that work, just in this case, is we're integrating P dV, where P has to be an equation. And in this term, we have constant. But what we can do is we can do this. We can actually take 0 and multiply it by V, because V is our symbolic form, our equation. Now, when you do this, this shouldn't give you an error because now you're integrating that equation with respect to V, okay? And so it actually gives you the correct answer, all right? Now, because it says X, it doesn't really know. So let's put V. So we're going to integrate with respect to V, okay? Now it should give us times V, okay? Because we're integrating the equation, and this comma says with respect to whatever variable. So that variable we want is V, okay? So that's that. So now if we go back up here, and I'm going to change this to equation, okay? But I'm going to integrate from our limits. So V1 to V2, and that's going to give us the work, okay? So it's running all the stuff above. I could probably highlight all that, okay? So it gives us 202,650. That's the amount of work or joules that is being done to move that piston, how much work you need to do to move that piston at constant pressure, okay? So just a practice of, if you have a constant and you want to integrate that, well, then just put 0 times that variable, okay? Cool. All right. Now let's look at differential equations, okay? And I'm going to highlight all of this and just delete it, okay, to make it quicker. Okay, I could highlight it all and comment it out, but then it gets a little messy. So I'm just going to delete it all, okay? So here we're going to go. We're going to solve dy dt equals 0, okay? So Matlab, this is a differential equation. If you're not familiar with this, then you probably want to skip this part. But a differential equation is basically an equation that you need to do some calculus on. And what you're trying to look for is, you see how y is on the top and then t is on the bottom? This is kind of going to give you an equation where it has y on the left of the equal sign and something on the right of the equal sign, okay? So a differential equation has derivatives, first order, second order derivatives, and there's rules on how to solve those, okay? Now, again, if you aren't familiar with this differential equations, I would probably skip this part, okay? But if we're trying to solve this differential, this is a derivative, and the derivative is set to 0, okay? Matlab has a built-in function called dsolve, okay? So we're going to write dsolve, and then what we need to do is we need to identify that this is the derivative, capital D, with respect to y, okay? So dy here, and then it should give us an answer, okay? So when we find this, okay, when we integrate this, this is an actual way to do this, okay? This will give us just a constant, okay? Because when you integrate 0, it's just a constant, okay? Meaning if you take the derivative, which is dy dt, okay, equals 0. So what they're saying here, and let me show you, is they're saying that y is equal to c1, okay? So when you integrate, sorry, when you take the derivative of that, it's 0, okay? So dy dt equals 0, okay? Because there's no t here. Like, it's just a constant. If we had multiplied by t, then the derivative would be c1, okay? But we had 0. Okay, so this is how you write this. Now, let's say we want to do this. Say we want to solve this equation, this differential equation, which is mass times the second derivative of x with respect to dt squared plus kx equals 0, okay? This right here is really mass times acceleration plus kx equals 0, okay? This is really looking at a mass that's attached to a spring that's attached to a wall, and you pull the mass back and it vibrates back and forth, where you neglect friction and air drag, okay? So it's vibrating back and forth. So what you're doing here, okay, is in this case, you have to break it up into 2 linear equations, okay? So the first equation that you're going to do, all right, is acceleration basically is dv dx, okay? not dx dt, sorry. Okay, comment this. So acceleration is really dv dt, which is the derivative, okay? So if you plotted velocity and time, the slope of the line you would get is acceleration. And the other one is velocity, which is dx dt, okay? So if you plugged this into here, okay, you would get d dx dt divided by dt, which is really d squared dx, no, sorry, x divided by dt squared. Okay, this is actually squared. So these two are linear equations because there's no power to the two. Okay, so this one right here, this is saying the derivative or dx equals v, which is this equation. Okay, this is how you do this. This is the basically saying the big derivative, which is these d's. Okay, and then the other one is basically saying we rearranged this equation. Okay, and I'll put it up here. We basically said that, let me do this here, should be divided by, oh, let's see here. So dv dt equals negative kx divided by m, okay? Because we can rewrite this as mass times dv dt plus k times x. Oops, and let me put it down here so you can see it all. Equals 0, and I'll review this, okay? So I said, well, acceleration is dv dt, okay? We know that this term, second derivative, is really acceleration. So I said, well, mass times acceleration, which is dv dt, plus kx equals 0. Okay, and what I did is I just rearranged this equation for dv dt. So I brought this to the other side, which is right here, and I divided by m. Okay. Now what I have here is this is the derivative. This is dv dt. Okay. Then I have minus omega n squared. That's just another way of writing this term over here. So dv dt equals minus omega n squared times x. Okay. Now, where omega n, there's just the square root of k over m. Okay. Basically, I knew what that non-dimensional number was, and I just plugged it in here. So don't worry too much about where I got omega n from. It's just a square root of k over m. Okay. Because if you square this, you get k over m. That's why I have omega n squared. Okay. So this equation right here is this right here. Okay. So we write again this d, big D, as this term here. Okay. And these are both linear equations. Now, this one and this one are our initial conditions. So if you know anything about differential equations, this is second order. So you need to have two. And this one is position, tells me if I have this mass with a spring attached to a wall, where I start this mass from the center point. Okay. Well, I didn't move it, but I gave it a velocity, which is the second initial condition, which is also this, the slope of the x versus t graph. Okay. So I'm giving it some initial velocity. Okay. And then I'm using dsolve. So I'm solving both of these equations at the same time with these initial conditions. And then look, I'm trying to get these values x and v. So x is position of the mass spring, and this is velocity. So if we run this, okay, we now have x and v. Okay, and if you notice, they're imaginary because this should oscillate. All right, now if we want to plot it, let me just show you. You can plot the solution. Let's see, I'll hit enter there, hit enter here. So this is what I just pasted in. I gave it omega n 10. Here's my time range. Okay. I'm plotting, holding on, putting my limits and my titles. Okay. And there you go. We got a plot of x versus t. This is position of the mass. Okay. So just to recap this. All right. This is probably the hardest part to learn. And if you're not familiar with differential equations, then I'd probably skip it until you are. But again, differential equations have derivatives inside there that you have to follow rules. And what you're trying to look for is a function. You're trying to look for, in this case, for dy dt equals 0, what y is as a function of t. Okay. And this one, we solved it and we got y as a constant, but it's actually plus 0 times t if you want to get technical. Okay. Because that is y as a function of t. Okay. And use the dsolve command because you're solving a differential equations. This capital D basically says that it's dy dt or whatever variable you're doing at the bottom. Okay. Now down here, what we had is this right here is a differential equation that solves for a mass attached to a spring that's attached to a wall. And if we move it back or give it some initial velocity and let it go, it'll oscillate back and forth on the table where there's no friction, no air drag. Okay. So this is really Newton's second law, mass times acceleration, and this is spring force. Okay. So these are all, this is the summation of the forces, and this is your MA term. So if you remember from Newton's second law, summation of forces equals MA. So what we have here is, this is the fundamental equation. This second derivative of x with respect to t is really acceleration. Okay. But acceleration, and sorry, I'm kind of skipping a little bit down here, but that's fine, is also dv dt. It's the derivative of v with respect to t. Okay. And if you have velocity, which is dx dt, and you plug that equation into right here, that's what I did right here, that's where you get d squared x dt squared, which is this term right here. Okay. Well, what you need to know is when you want to solve anything like this numerically, solving using Matlab, whatever, you can't do second order like this. You have to split it up into two first order, meaning the derivative, there's no twos. Okay. So we broke this up and we said, well, we know that acceleration is velocity with respect to time, dv dt. So I plugged that in here, and then I rearranged it to solve for dv dt equals minus k times x over m. Now, that's velocity. This equation right here that I'm highlighting solves for velocity as a function of time. But you also need, okay, to know this equation, which I'm just going to rewrite it so it's kind of in the same format. This equation, okay, dx dt equals v. So we can solve for x, which is the position as a function of time. Okay, so this equation and this equation, or really, you'll see here that I broke it down in omega n, another number, another kind of variable. This equation and this equation are used in the dsolve to solve two first order linear equations. Okay, so dx equals v is this equation. So we're solving for x versus t. And over here, this is dv dt equals minus omega n squared times x. Okay, that's the second linear one. These two are my initial conditions because the power of the main equation here is to the 2. So we need 2 initial conditions. This is position of the mass, and this is the velocity. So we could give it some initial position. So here, say right here is the mass, and we pull it back 0.2 meters, and we let go with some initial velocity. Or we don't give it any initial velocity. We just say we just pull the mass back and let it go. It's going to vibrate and then stop. Okay. So if you had like a third order differential equation, you would have 3 first order equations and 3 initial conditions that you would solve for. Okay. So I used dsolve. I solved it. This is my solution, but I need to use the dot or the get command to get x and v. And then I go ahead and pick some values for omega n and t, which are my constants, and then I plot it. Okay. So if I run this, this is now, oops, I forgot to close all. Okay. And this is what happens when we give it an initial position. And look, at time of 0, look, it's 0.2 because that's what we picked. Okay. And it just keeps oscillating back and forth. Okay. Now, it'll keep oscillating because we're assuming no friction, but if there's friction, it will oscillate and stop. Okay. Then there's actually another term in here that you'd have to plug in. Okay. So it's pretty cool that we can do this. And if you look, x's versus t, that's because we're solving for a function. Okay. If we look at x here and we look at v, these equations are functions of time. Okay. So as time changes, this is what happens. Okay. All right. So that's all I have for tutorial 9 on symbolic. Hopefully it will help you. If you're doing calculus, derivatives, integrals, or trying to solve, this is the fastest and most efficient way that I use it. All right, thank you, and I will see you in the next one.